So we're going to introduce the concept of chemical equations in Chapter 8. And we're going to be looking at chemical reactions. If ever there's a chapter that you want to be present and live in, it is no doubt Chapter 8. Because we get to see all kinds of different chemical reactions. But unfortunately, that's not the world we're living in for the next 3 weeks at least. So what I'm going to try to do is try to get videos of these demonstrations that I would show you live. I've considered going in and trying to make them. Unfortunately, it takes like a crew to do, and the building is fairly empty right now, and I just need some help. So if I can enlist some help for filming purposes, I can do that. Otherwise, I'm going to be relying on what others have done before. I have a picture of your notes up. I've posted your notes in the files for teams under Chapter 8, and I went ahead and included them in this assignment. Again, when you are doing the notes, you can either print these out and you can write on them directly. That's probably what I would do. If you're more digitally inclined, you can use the drawing tools. And again, if you can't remember the drawing tools, there's a draw menu up here in Word. You click on that, and then you got some pens over here to click, and you can manipulate them and make different colors, and you can write in different sizes if you want. And so you can write in there like that. That's a little bit too big for my taste, so I'd probably shrink it down a little bit there. And there we go. And so you can write on the lines, and then you can save it to your own device. I wouldn't save these to Teams per se. I would download my own copy and save them if I were going to be doing that. As you're taking the notes, what I would probably end up doing, and I need to back up here a little bit on this, what I would probably be doing is I would watch an entire slide, and then I'd write down all the information on that slide, and then go ahead and play the video and watch that whole slide, pause the video, write down all the information that's on that slide, and then continuously do that. I wouldn't write as the person is talking. I would just watch for a while and then write that stuff down at the end of the slide. So our objectives here, we're going to talk about chemical reactions. We're going to learn when they occur, what are their indicators. We're going to learn how to write them. We're going to end up balancing chemical reactions. The fun part, I think, is being able to predict it. I will be able to give you the reactants of a chemical reaction, and you tell me what gets made based on a list of a few rules. And then lastly, we'll be using the activity series in order to tell, in its most basic form, whether a reaction will occur or not. There's a lot of other ways to do that, but that's the easiest for us. So you can break down chemical reactions into one of two types. The first type releases energy, and I have a picture of here, and I got a demo I'll show you of this. These are exothermic reactions. They release heat, they release sound and light, they feel hot to the touch, so heat is coming out of them. The other type of energy relationship on the reactions are endothermic. Endothermic reactions feel cold to the touch. They actually absorb energy. There's not super many endothermic reactions I can show you, but I did have a one good demo that worked. The bad news about that is that you can't even watch a video on that because you've got to be able to experience the temperature change. So at least on the exothermics, you can know, like on the picture, hey, that looks hot because there's fire and stuff coming out of that. All right. So chemical reactions don't just necessarily happen on their own, or what you could call spontaneously. Most chemical reactions need some kind of energy to trigger them, and that's called activation energy. So here on the screen I have a graph here of energy versus time, and at the beginning you have your reactants at a certain energy level, and at the end of the reaction, over here on the right, they are at a different energy level, and you'll notice that the energy level has went down. You have this big bump right here. This big bump is called the activation energy. This is the energy needed to trigger a chemical reaction. If you just take a match and hold the match in your hand, nothing happens. We need to activate that chemical reaction, even though everything for it is available to the match. It's got all the elements in it needs, plus the oxygen in the surrounding atmosphere. So in order to trigger it, you have to take that match and strike it against a strike plate. That's the activation energy. So the activation energy kicks off the chemical reaction. So these bumps here represent the chemical reactions. So here's another one. And I mean, what can you say about this? Well, the bump isn't as high, which means the activation energy isn't as much. And so when you have lower activation energy, these things happen more spontaneously. So chemical reactions that appear to happen just spontaneously, well, that's because there's enough energy in the atmosphere to trigger them. You cool down the atmosphere, there may not be. And then both the first two are exothermic, so the energy is lower at the end. Here's an example of an endothermic reaction where the energy is higher at the end than it was at the beginning. Alrighty. So in the demo I want to show you, it involves a pair of steel bearings that have been rusted, or possibly even iron bearings that have been rusted. And if you take these large balls together and you hit them, a lot of energy is released in that particular chemical reaction. It's enough so that when the balls hit each other, there's enough energy there to burn paper. So there's lots of frictional energy available. And the reaction we're going to be looking at is what I call a mini-thermite reaction. Most people call it a mini-thermite reaction. And it's a reaction of rust, which is on the iron ball bearings, and aluminum. And aluminum and rust, when they come into contact with each other, should be very reactive. But if you just lay aluminum on top of rust, nothing happens. You got to have that.
It's really simple. The thermite reaction is iron oxide reacting with aluminum to form iron and aluminum oxide. Iron oxide is rust. So I have two rusty milling balls that a good friend of mine has given to me. And you can see there's pretty rusty. The rustier, the better. And then you need good old-fashioned aluminum foil. I bet you never knew that aluminum foil could have such a neat use. Now what I do is I'm going to set one of these down, and I'm going to wrap up this iron ball, rusty iron ball.
So like I said, when aluminum and rust come into contact, it's usually an extremely violent reaction. But the aluminum is touching those rusty ball bearings, and there's no reaction at all because there hasn't been a kickoff of the activation energy. The activation energy will be where he bangs the two ball bearings together, creating frictional forces to trigger the reaction.
With this aluminum foil. And then the kinetic energy of the two things hitting together can be used to spark, if you will, this chemical reaction. It's pretty, you can, it's
Now you can see that the reaction has caused giant tears in the aluminum foil because there's so much reaction. The sparks that you're seeing flying off of there are molten iron because iron is a result of this. You're taking the Fe, let's see, that'd be Fe2O3, that'd be rust, and you're getting the iron out of it and you're making aluminum oxide and iron, basically.
Pretty violent. You can hear it, obviously, and you can see it.
That was a dud. There we go.
So, I'm going to turn off the lights and see.
Alrighty. So that is your reaction there of mini thermite. A lot more dramatic in person, but is what it is. And again, that reaction doesn't happen unless there's some activation to it. And so that would be representative of like this first graph right here. You're going to have a lot of energy, the two ball bearings colliding together to generate enough heat to actually kick that reaction off. Alright, so part B, indicators of chemical reactions. And this is where I'd be showing you a bunch of different demos. And unfortunately, we don't have ability of those demos here. So what I'll try to do is look these up on YouTube and produce them for you. So the first one of these is indicators of evolution of heat and light, which you saw on the previous video with the sparks and the sound. And I usually use the whoosh bottle example, which I'll show you a video of. Alright, so let me show you what I got prepped up here. We have these large bottles that are used for drinking water, and this person doing the demonstration, he's going to be pouring in some ethyl alcohol. You could also use isopropyl alcohol, and I'll let him take over.
Of ethyl alcohol, okay? Now this is 95% ethyl alcohol, so it is very, very concentrated, if you will. All right.
Now, notice how he did not fill the bottle with the ethyl alcohol. With alcohols, it's not necessarily the liquid that's flammable. It is the vapor that's flammable.
Also very flammable. Jay, what I'd like you to do is pick that jug up and sort of swoosh that liquid around. So what we want to do is generate some vapors inside the jug. And if you can, carefully tip it almost on its side and rotate it. But don't let any of the liquid come out. That's perfect.
Sure.
We want to coat the inside. We're going to build up lots of vapor because that's what we want to ignite. We're going to show you how flammable some vapors can actually be. So tip it totally upright. A little bit of liquid comes out. Let it drip for a second. Perfect. Go ahead and upright it. We'll take this away. And now we've got a very flammable mixture of gas inside there. I'm going to give you some matches.
Okay.
You've got a pair of tongs for safety. Okay, so let's light the matches here. And once you get them lit, give them a second. And then we're going to have you come over the top of the jug and just drop the matches into that flammable mixture of gases.
Right, here we go. 3, 2, 1.
Woo! Yeah. It ignited. You get that.
All right, so you saw that giant whooshing effect as the fire came out of there. Now, I also showed this using just standardized pop bottles because it's kind of fun to do the pop bottles. And see if we can get the whooshing effect here back.
Into that flammable mixture of gases.
Right, here we go. 3, 2, 1.
All right, so here you got this giant explosion in here. You've got the gases expanding because of the heat, and that's why you got this jet of fire coming out here at the top. Now, like I said, I also do this with normal pop bottles. And with the normal pop bottles, what I'll do is I'll immediately close it off. It's so hot inside, the atmosphere will compress the bottle. One of the products to this is actually water vapor, and you trap the water vapor inside the bottle, and you actually form a cloud, a different, actual cloud of water vapor that's condensing on the vapors that were left over inside of there. All right. So that's the whoosh bottle. Our next reaction here is the formation of a gas. The formation of a gas. Let's see here. You probably saw that on that last video with the whoosh bottle because there would be a cloud of gas if you could see it. And then the one that I do is the formation of chlorine gas. I'll see if I can find a video of chlorine gas being generated using bleach and an acid. And the chlorine gas I have here is being in green. And it's green because chlorine is a green-colored gas. Alright, so I couldn't find a good one that showed the chlorine gas very well, but I have this reaction here, which you'll get to see the evolution of a gas easily with. This is copper that's at the bottom of this conical flask here, and the person on this side of the fume hood is going to be adding some nitric acid. Copper is usually unreactive with different types of acids. Nitric acid is one of those exceptions, though. So what he's going to do is he's going to pour in the nitric acid, and it's going to react with the copper. This is inside a fume hood. The fume hood is on. This is concentrated nitric acid. And luckily we got that ad that pops up. That's cool. And the nitric acid is reacting with the copper, forming copper nitrate. And if you can barely tell, this is a green solution down here, indicating that the copper is going in solution. People will say that the copper is being dissolved. Well, it's not exactly being dissolved because there isn't copper just in the solution. It's copper nitrate that's being made too. Although it's kind of copper ions, so I guess, okay, it's being dissolved in some form. But what you should notice is you got this brown gas. It's extremely poisonous. That's why we're doing this in the fume hood. And I'm going to kind of speed this up a little bit here. And now he's going to pour some water in here. And this is pretty cool to see live, is that the pouring of the water turns that dark green solution a very nice, what I call an ocean blue. So you're seeing not only color change here, you're seeing the evolution of a gas, and if you could touch it, it would feel very hot. So you got 3 indicators of a chemical reaction right there. All right, so you saw heat being, well, you didn't see heat, but there was heat being produced. You had the formation of a gas. You had a color change down here. That's this reaction down here at the bottom here, this nitric acid and copper. Formations of precipitates. You've seen precipitates being formed before, and so there's a difference between a precipitate and a color change, and the way you tell the difference between those is using a centrifuge, and that's also a demo that I would do to show you the differences in centrifuging. All right, so let's talk about chemical equations. You've seen these before. The items on the left side of the arrow are called the reactants, and the items on the right side are called the products. The arrow in between means yields. You could switch the arrow around so it points to the left, in which case the right side are the reactants and the left side are the products. But standard, it goes from left to right. So that means yields. And the coefficients in front of here are the number of moles or the number of particles. So the way you end up reading this reaction is 1 mole of lead chloride, in which case this would be lead 2 chloride, and 1 mole of sodium chromate will make 1 mole of lead chromate and 2 moles of sodium chloride, or 1 molecule of lead chloride and 1 molecule of sodium chromate will yield 1 molecule of lead chromate and 2 molecules of sodium chloride. And so you can talk about amounts of substances being produced here. In chemical reactions, there are some elements we got to learn how to write correctly. The first of these are what I call the Magnificent Seven. These are elements that exist in nature not by themselves as a single atom, but as a diatomic molecule. Diatomic meaning, of course, 2 atoms. And so here we have H2, N2, O2, F2, Cl2, Br2, and I2. These are the Magnificent Seven. I call them that because they actually form the number 7 on the periodic table. So here you have nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and then over here in the upper left, you gotta remember your hydrogen. So anytime you talk about chlorine gas being needed or chlorine gas being evolved, you don't just write Cl, you write Cl2. Because they're diatomic. And there's that number 7 there if you missed it. All right, let's talk about different types of ways to indicate things happening in a chemical reaction. The arrow means yields or forms. The double-ended arrow means reversible reaction, which means it could go both ways, which a lot of chemical reactions are both ways. An S in parentheses or a down arrow, as in NaCl with an S, is talking about a solid or a precipitate. So maybe one of my reactants is solid NaCl that I add to something. An L in parentheses, as in H2OL, is telling you to use liquid water. And a G tells you to use gaseous water. So you're talking about water vapor. So we can have water vapor, you heat it up. And AQ tells you that the substance is dissolved in water. So NaClAQ means an aqueous solution, sodium chloride that has been dissolved into water. An arrow with a delta over it or a temperature. The delta just means to heat it, and the temperature means to heat it up to a certain temperature and keep it there. The delta is supposed to represent a little flame, like from a Bunsen burner or a candle. And a chemical symbol or formula written over an arrow is telling you that a catalyst is being used. Alrighty. I believe this ends us. Yep, balancing equations is next. So we will stop right here. And if you have any questions, let me know in the comments. And look out for your next assignment.